Regarde si ça marche. Okay.
Okay, so hello everyone. My name is Alonso Silva. I work at Bell Labs, and today I'm going to speak about reasoning models, and in particular about using the model's certainty in order to improve results, save tokens. Yes, so this is what we're going to do. And so first I'm going to start with the phrase by Benedict Evans, in which he speaks about are better models better? And he says, like, every week there is a new model. Today there is OpenAI who's dropping a model. Grok was launched today also, and they are going to probably launch Gemini something today as well, because in order to to kill OpenAI's announcement, they're going to drop another model. But is another model better than the previous one? And we usually, when we think about these models, we think about having better answers, but this is usually not what people think. So better, it's not, there are many occasions in which better answers are not better. There are only right answers or wrong answers. So this is what this post is about. And in particular, I'm going to speak about self-awareness of these models. So one of them is related to, in certain domains, let's say in justice or in medicine, a wrong answer are much worse than an I don't know answer. So if I condemn someone for 20 years to jail, it's probably worse than to say I don't know actually if I don't have the judgment in order to deliver that judgment. And I'm going to make a controversial take, which is basically from this work, which is that the language model mostly, and this mostly is between, know what they know. And this is what we're going to explore today. Okay, so I'm going to speak about a particular data set, which is AIME. I think most of the people in the area know it, but not necessarily everyone. So AIME is a 15-question, 3-hour test given to high school students. And they are usually the good students from high school. And they are given 3 hours in order to solve these 15 questions. And there are two tests, so you go there, you take the test, and there are two possibilities, IME 1 and IME 2. So in total per year, there are 30 questions. And this is an example of a question. There are 8-digit positive integers that use each of the digits from 1 to 8 exactly once. Let n be the number of these integers that are divisible by 22. Find the difference between n and 2025. Answer. Okay, so they get 3 hours for 15 questions like this. And another question, for example, there are n values of x in the interval between 0 and 2 pi, where f of x is equal to this sin of et cetera, equal to 0. For t of these values, the graph is tangent to the x-axis. Find n plus t. And one of the characteristics, so this is, of course, 149. And one of the characteristics of these problems are that all the questions go, the answers go from 0 to 999. So that's very nice, because you know that, okay, you have 1 over 1,000 probability of guessing the answer, but also you know a good way to verify the answer. So this is very important for what I'm going to talk now. So one is, so last year in September, they announced O1. I don't know if you have followed, but O1 was basically the best model at the time was GPT-4. And in this IME dataset in 2024, it was getting around 12%, a little below 12%, because there are two bars. There is like the dark one, and there is another one above. And in particular, in the IME dataset, it was getting around 12%. And that was the best model up to September last year. And in September, OpenAI dropped O1, and O1 was able to get around 80%. So the O1 preview was getting 40 something, and the other was like getting 70% in this dataset. And they also, OpenAI, when they dropped this model, they also showed the following graph, which said basically, as you train this kind of model, these reasoner models, the more you train them, the better they get. And a lot of people in AI safety became crazy, because they said, okay, if I train my model enough, I assume that there is a line there. It means that the model will reach 100% for any task. That's not the case. It saturates, but but you can see that there is a nice straight line. And this line is log scale, so it's important. So the time is, it means that basically if I give the problem, the model a task and I let it run for 200 years and then at the answer he can be 42 and it will be, so this test, train test compute and test time compute will be given the time that I give the model to think. And at the time, I say, okay, nobody can. The open source community and the open web community, we said, okay, that's it. OpenAI solved this, and then DeepSeek appeared. I don't know if you follow, but also the DeepSeek was a big thing, and it appeared in the end of December, and it dropped NVIDIA around 20% of Nokia companies. NVIDIA dropped the price of NVIDIA dropped like 20 Nokias, and the DeepSeek was able to manage to get the same kind of curve. You can see the red curve here for IME, in which that this is the average number of thought tokens per problem. And this is the accuracy. And similarly, the model, as you give it more time to think, it gets better. So this is for pass one. Then there is majority voting, but so we have voting for fun. But it's we are worried about pass one. Pass one means I ask the question once. Okay, and I'm going to, for this study, I'm going to use, I use these three models. One is DeepSeek, the other is Quen, and the other is P4. Now there is P4 mini reasoning, it appeared today. And there is pass one score means I ask the model once and I get the answer once. And the first thing we did, we said, okay, let's replicate this graph to see if it works. And we were able to get the same kind of graph. So we are forcing the model to think longer. We are basically using a logic processor in order to make the model think longer. But you can make it without logic processor. You just remove the last token and make it think longer, and the model will perform better. This is for IME in the thinking time. And then we said, okay, let's say that the model is able to say, I don't know. And this we needed to model. So we said, okay, let's consider that we will score the model for a certain query +1 for correct answer, 0 for abstention, and -C for wrong answer. In many countries, in Chile for sure, and but in not, I don't know if in the US, but I think that in many countries they also consider that if in a test you get wrong answers, you are penalized. So in Chile, if you have 4 wrong answers, you get 1 answer less. So that will be C equal to 0.25. And so the idea is that students don't try to guess. The students, if you don't know, it's better you say, I don't know. So in order to compute the score of the data set, it's just going to be the score for the sum of all the scores for all the queries. So it will be equal to the total correct number of questions minus C times the total number of incorrect questions. And if we have C equal to 0, this is equivalent to accuracy. Basically, you're just counting the number of correct answers. If you put C equal to 1, this will be like balanced score, and C equal to 2 could be a conservative score like for law or medicine. The idea is that you want the model to say, I don't know, if it really doesn't know. And we're going to define certainty. The idea was to test if the model knows what it knows. So this is what, and we define it as in this way. But the important thing is not the definition. Is if I just show you, the model will answer. So the model will think, because this model think, and they think for a long time. But after 10 minutes of thinking, they will give an answer. And the answer, we know that it's going to be of this shape, or at least this is what we hope. The model will give an answer, which will be a number, and the number should have 3 components, 3 numbers, 204, for example. And the model will give you can look at the logics, and you will be able to get what's the confidence that the model has about each of these numbers. And let's say that the confidence was 98% for token 2, 97% for token 0, 99% for token 4. Therefore, we take the minimum of all the 3 confidence. So you take the maximum because you take the maximum logic, and then you take the minimum, which will be the minimum of this. Why I take the minimum? Because basically, in many occasions, if I ask you a question like, okay, I don't know, let me think, like 78 times 2, you know that the first digit will be 1 very easily, but then you don't know what's going to be the other 2 digits if I ask you very fast. So the idea is the model in some occasions, for example, in other data sets, it gets some tokens, they get it very easily. So you don't want to bias your measure by this. So this will be so that's why we take the min max. So our algorithm is going to be the following. We basically compute the certainty and we put a threshold. It's not that important, but the idea is that we put a threshold in which we say the model is certain or not in order to answer a question. And if we put this certainty at threshold, we get the following. So the model start to guess, this is about, we basically probe the model at certain occasions. And if the model answers correctly, this is going to be the green bars, and then it's going to be the red bars. And here the model starts with quite a big number of green bars. And actually later, if you just let the model run, all of the rest will be red. So it should go to up to 30. It should be red. The model basically gets the correct questions, not perfectly, but he's certain about the questions that are at the beginning and that they are correct. And a few of them are wrong, but most of them are correct. And then it starts getting wrong. Now, this may be related also to the model that some of the questions may be more easy. And this is for sure something that it has to be taken into account. And then we said, okay, IME 2024, DeepSeek was from 2024, so perhaps it's already in the dataset. So we said, okay, let's test the same thing in IME 2025, which is this year. DeepSeek was released last year in December, which means at the end of December, which means that it has not seen the question from February this year. And we get the same kind of behavior. So basically, we managed to get the model to say, I don't know. And if we manage to get to put a threshold in which he can say, I don't know, it gets much better score. So what other graph we have? We have the following. So if we put the model that the model will in any case answer, we don't lose anything with our method. So that's important. We basically get the same as if we just let the model run. But we, for different values of C, if the model is able to say, I don't know, we get much better. So the baseline is the red one and the blue one is ours. And it gets much better already at 5,000 tokens. I don't have a plot of the thinking tokens, but we save around 10 and 20% of thinking tokens, which is important for people who work about energy efficiency or trying to minimize the quantity of energy of these models. You can also save a lot of thinking tokens with this method. Basically, it's some way of selecting what's a good for how long you should think. So conclusions, certainty-guided reasoning saves thinking budgets while improving the average pass one score. And as future works, we are testing of many different things. So one of them is flashing versus summarizing thinking. You could think to let the model think for a long time, then summarize his thinking, then continue thinking, summarize his thinking, continue thinking. The idea is that at some point he will be confident enough in order to answer the question. The second is to have a specialized critic model. This we have implemented. The idea is that you will have somebody who will give you a reasoning, but you will have somebody, another model who will say, okay, is this reasoning sound or not? And this other model will give you a score. The other is curriculum learning, which means teaching the model first to solve some sort of questions, and then the idea is to make it more and more complex. And the fourth one, it is related to using the certainty measure in order to train models doing reinforcement learning with this certainty. So the idea is not only using verifiable rewards, but using the certainty of the model itself in order to score the output of the model. So that's it. Short question.
So this is very nice work, but I'm just thinking a bit bigger, more broadly. You're working on solving math problems, right? So maybe thinking a little more helps, okay, or you can optimize that. But a lot of where this gets dangerous is when these LLMs have to answer I like to call them squishy problems, you know, so you ask me, should I trust President so on, right? Or, you know, whatever, or should I take vitamin C? Will that help me to get over my cold? Where the answer is maybe, it depends on 20 things about your body and your health and so on.
Mhm.
So do you think that there's an application of this work to solving these other kinds of softer problems, which are not strictly mathematical, that
Mhm.
LLMs have to answer?
This is so most of the research now is doing about verifiable rewards, which means you can verify the answer because and this is why I put P versus NP. The idea is that we guess that verifying is easier than constructing the thought. But the idea of using the certainty of the model itself is in some sort of, in this kind of question in which there is not verifiable answer, try to use the certainty of the model itself. It may be a problem because these models usually are overconfident. So yeah, this is why we are exploring, but we don't have an answer to this question. But yeah, it's interesting.
Yeah. Okay. We can talk more of the break.